Then. Right.
Okay, we're recording now.
Oh.
Right, we'll just start now then. Welcome everyone to another CAS webinar. So just a reminder that we have our belated AGM on the 29th of September. And Robert will no doubt be preparing the agenda for this, and either he or I will attach it to an email and send it to everyone beforehand so that you can print it out. I have booked webinars and speakers right up to the 14th of December. As I said last time, we decided to keep these going till the end of the year to keep everyone safe. Our next speaker will be on the 5th of October when we have Pete Williamson, Remote Telescopes for Public and Educational Access. Right, so tonight we have Eddie Carpenter with an anniversary talk. This is going to be 2 to 3 minutes. Then our main speaker, Roy Bryce, the Geology of Venus. So let's give Eddie a warm CAS welcome.
Thank you. Right, September the 1st, 1974. No, any luck? Anyone? No, it was Mariner 10. Does anyone remember Mariner 10?
Yep.
It gave us our first close-up views of the planet.
Mars?
Not Mars, no.
Venus.
Mercury.
Oh, Mercury, right.
The first view we had showed virtually nothing, but the second view with Mariner 10 was a much closer flyby, and revealed what it looked like the moon, basically. So that was the anniversary. This day in 1974, Mariner 10 did a flyby of Mercury. For my Cornish astronomer, I expect you've heard of Sir Humphrey Davy.
Yeah. Yes.
He was basically not an astronomer, but he was a chemist. He was interested in elements, particularly elements on the sun. He got some of this information from his younger brother, John Davy. That's an astronomer I'm going to talk about, John Davy, 1790 to 1868. He did most of his observations. In fact, you know that Humphrey Davy was born in Penzance, went to the grammar school that I went to. And obviously his brother, John Davy, was also born in Penzance. And they worked together for a while, doing some astronomy, but mainly chemistry. John was mainly interested in his work, in his brother's work on elements. And eventually Humphrey Davy invented the Davy safety lamp.
Safety lamp, for the miners.
That's right, the miner safety lamp, because there was a lot of mining going on in Cornwall. And a lot of deaths, so they invented the miner's safety lamp, which worked actually about 90% of the time. It was still a risky thing to use, but his brother actually carried on doing some chemical work to help Humphrey. But he's more interested in astronomy, and he became a medical doctor, and did most of astronomy actually with a bit of a sensible place. He went to the West Indies to do his observations, and to Malta. He listed tables of stars, their positions, just details really, ephemera about the stars, and then some work on the solar system, the planets. Most of his work actually is in the Royal Institution or in the one of the libraries in Penzance. They have a lot of work there done by John Davy. So it was about 2 years ago, I thought I'd go in and have a look. Of course, when I got there, the place was all closed because they're actually removing some stuff, putting him in another room, redecorating this, be open in about 2 weeks' time. I went back about 6 months later, they hadn't done anything, it's still going on. So if anyone is down in Southwest Cornwall, if we're ever allowed to go down there, call into Penzance Library, and they've got all the stuff moved up to there now. So that's the Cornish astronomer for this time. John Davy, born in Penzance, younger brother of Sir Humphrey Davy.
Okay.
Anyone, any questions?
Mm.
He didn't become a proper professional astronomer. You could call him really a big amateur astronomer, I suppose, really. But he did a lot of work. There's a lot of work in those documents hidden away in the library, which one day we might be able to see. But there's quite a lot in the Royal Institution in London. They have a lot of his work as well. A lot of his booklets, tables, masses of them, apparently. I didn't know much about that until a few days ago.
Right.
Mm-hmm.
Okay,
Very interesting.
Yep, very interesting.
Ready?
everyone knows about Humphrey Davy, but not about John Davy.
Aye, because I'd never heard of John Davy. You've always
Yeah.
heard of Humphrey Davy.
Yeah, well,
Because-
you've heard of him now.
Aye,
Yes.
because my late uncle was a miner, you know.
Yeah.
So he always mentioned he talked about the history of the mining and that, about the Davy lamp and that, you know. So
One of the gases he worked on was phosgene. He didn't discover phosgene, but a lot of people actually blame him for distributing phosgene to the army. I'm not sure about this story, because phosgene, I believe, is one of the main gases used in warfare. Gas warfare.
right.
And they put a lot of blame on John Davy for I wouldn't say inventing it, but perhaps discovered it. I don't know. So that's one thing that's against him. In favour of him is his astronomical work on observations of the stars, in Malta and the West Indies. But what's against him is actually his work on phosgene. He did chemical work, the same as his brother. I reckon his brother probably did something about it. Do you know which is the most poisonous gas in the world? When I was reading about this a few days ago, it's actually nitrogen. If you actually got pure nitrogen, you wouldn't last so long.
Right.
Yes, but you die in ecstasy. Did you not see the documentary years back with Michael Portillo?
No.
And he went over to Sweden to the Air Force training chamber where they depressurized them and then fed them pure nitrogen, and you get nitrogen narcosis, raptures of the deep, as they used to call it. And they had to stop the experiment because he was so away with it and enjoying it so much that he would have died in a minute more.
Yeah.
All right.
Yeah.
What?
Well, that's what it said on Wikipedia, that
Nitrogen's the best gas if you want to do it, because it's natural in air along with oxygen. So the body doesn't tend to go against it. If you feed helium, which they sometimes do to kill animals, then the bodies can react against it, because helium's not a natural gas to the human body.
All right, okay.
Right then, okay, thank you.
Right, thank you very much.
Thanks very much.
Thank you, Eddie.
Yes, thank you, Eric.
That talk you got next time by, was it Williamson?
Aye, Pete Williamson.
Yeah, I just heard it actually on, he did it on, can't remember if it was the Bristol site or the Cotswold site a few days ago. So I might not attend that one. I will give an anniversary, but I listened to his talk a few days ago for the, I think it was the Cotswold Astronomical Society. It was quite a good talk, actually.
Aye, it is, aye. I heard it a long while back, you know, but with my foggy brain I forget, so it's so it's all like new to me again.
Okay then.
Right,
Thank you again.
thank you again.
Eddie.
Yeah, keep taking the pills.
Yes, we will do. Right, now we're on to our main speaker of the evening, our member Roy Bryce, with his talk, The Geology of Venus. And it's quite appropriate considering there's been stuff lately in the news and on the sky at night about Venus and the phosphine in the clouds and that in the atmosphere. So we'll learn quite a bit about the geology of Venus, right? So
Thank you. Give me a second or two and I'll just try and do the share screen stuff. If somebody can tell me that it's working correctly as well, that would be helpful.
yes,
Yes, it's there. It's
Yeah.
there.
Actual,
right.
try
I'll
to get the
just mute
slideshow to start.
myself.
Oh, that's it. That's better. Okay. Just make sure this thing's working. Right. Hopefully you've got a spinning Venus in front of you just now. So in the best history of physics lectures, we'll have a few wee facts to start off with. So Venus's orbit's about 108 million kilometers. It's got an orbital period of 225 days. And the day on Venus lasts 243 days. So this kind of first weird thing you see is that the day on Venus is actually longer than the year. And it's got an axial tilt of only 2 degrees compared to Earth's 23 degrees. Venus is roughly the same size or the same diameter as the Earth. It's got 87% of its volume, 81% of its mass, 90% of the gravity of Earth. It's got an iron core, about 1,100 miles radius. However, it's slightly odd, Venus rotates in the opposite direction to the Earth. So Venus is a terrestrial planet and it's sometimes called Earth's sister planet because of the similar size, mass and proximity to the Sun and the bulk composition. However, it is radically different from the Earth in other respects. It's got the densest atmosphere of the 4 rocky planets, consisting of more than 96% carbon dioxide. The atmospheric pressure in the planet's surface is 92 times that on Earth, or roughly the pressure you'd find 900 meters underwater on Earth. And as I said, it has this retrograde rotation. Unlike most other planets in the solar system, which rotate on their axis in a counterclockwise direction, Venus rotates clockwise. It also rotates very slowly, as I said, taking 243 Earth days to complete a single rotation. This is not only the slowest rotation period of any planet, but as I said, it means a single day in Venus lasts longer than a Venusian year. So if you lived on Venus, your days would be longer than your years, and the sun would rise in the west. Scientists have suggested that it started off rotating counterclockwise like all the other planets, then slowed down to be almost static before starting to spin clockwise like it does now. Some astronomers think that the sun's strong gravitational pull on the dense atmosphere of Venus and the atmospheric tides this would create, along with the tidal pulls from the other planets, could all have combined to reverse the planet's spin. This idea of tidal torques, where the dense atmosphere on the warm, sun-drenched side of the planet is pulled away from the cold side, is one of the best established explanations for Venus's retrograde rotation. An alternative explanation could be that, like Earth, Venus suffered multiple collisions with other planetesimals during its formation. In Earth's case, this led to the formation of the Moon. In Venus's case, some think that the pieces came back together in such a way there were no moons but reverse spin. You just have to choose your favourite theory. It's hoped that when the Bepi-Colombo mission to Mercury does its 2 flybys of Venus, some additional data may be gained that help solve this enigma. Venus is on the just too hot side of the solar habitable zone. And as we'll see, this has made its atmosphere very different to Earth's. The similarity in size and density between Venus and the Earth suggests they share a similar internal structure, a core, mantle and crust. Like that of Earth, the Venusian core is at least partially liquid because the two planets have been cooling at about the same rate. The slightly smaller size of Venus means pressures are 24% lower in its deep interior than Earth. The principal difference between the two planets is the lack of evidence for plate tectonics on Venus, possibly because its crust is too strong to subduct without water to make it less viscous. This results in reduced heat loss from the planet, preventing it from cooling and providing a likely explanation for its lack of an internally generated magnetic field. Instead, Venus may lose its internal heat in periodic major resurfacing events, which we'll visit later. As one of the brightest objects in the sky, Venus has been a major fixture in human culture for as long as records have existed. It's been made sacred to gods in many cultures, and it's been a prime inspiration for writers and poets as the morning star and the evening star. Venus was the first planet to have its motions plotted across the sky, as early as the 2nd millennium BC. When Galileo first observed the planet in the early 17th century, he found it showed phases like the moon, varying from crescent to gibbous to full and vice versa. When Venus is furthest from the sun in the sky, it shows a half-lit phase, and when it's closest to the sun in the sky, it shows as a crescent or a full phase. This could be possible only if Venus orbited the sun. And this was among the first observations to clearly contradict the Ptolemaic geocentric model of the solar system. So how did Galileo manage to see the phases of Venus? On Earth, the solar wind is deflected by Earth's magnetic field, and our atmosphere remains relatively clear. The magnetic field is generated by the core of molten iron at the centre of our planet. To understand why Venus has a different type of atmosphere, we had to wait until spacecraft could visit and take direct measurements. In 1967, Venera 4 found Venus's magnetic field to be much weaker than that of Earth. The magnetic field is induced by an interaction between the ionosphere and the solar wind, rather than by an internal dynamo, as in the Earth's case. Venus's small induced magnetosphere provides negligible protection to the atmosphere against cosmic radiation. The lack of an intrinsic magnetic field at Venus was surprising, given that it's similar to Earth in size and was expected to also contain a dynamo at its core. One possibility is that Venus has no solid inner core, or that its core is not cooling, so that the entire liquid part of the core is at approximately the same temperature. Another possibility is that its core is already completely solidified. The state of the core is highly dependent on the concentration of sulfur, which is unknown at present. The weak magnetosphere around Venus means that the solar wind is interacting directly with its outer atmosphere. Here, ions of hydrogen and oxygen are being created by the dissociation of neutral molecules by ultraviolet radiation. The solar wind then supplies energy that gives some of these ions sufficient velocity to escape Venus's gravity field. This erosion process results in a steady loss of low mass hydrogen, helium, and oxygen ions, whereas higher mass molecules, such as carbon dioxide, are more likely to be retained. Atmospheric erosion by the solar wind probably led to the loss of most of Venus's water during the first billion years after it formed. To enable us to see details of the atmosphere on Venus, it's necessary to take observations in the ultraviolet band. This picture was taken from the Pioneer Venus orbiter in 1979. Venus has an extremely dense atmosphere composed of 96.5% carbon dioxide, 3.5% nitrogen, and traces of other gases, most notably sulfur dioxide. This forms clouds of sulfuric acid. The mass of the atmosphere is 93 times that of Earth, whereas the pressure at its surface is about 92 times that on Earth. As I said a wee bit earlier, a pressure equivalent to roughly a kilometre under the Earth's oceans. The surface temperature on Venus is 470 degrees centigrade. This is hot enough to melt lead, and one of the main reasons why getting a lander onto the surface is such a huge problem. Temperatures that melt lead means temperatures that melt the solder that's used to connect electronic components on the spacecraft. If you haven't got any connections, you've got no way of sending back results. It should also be noted that the high temperature is caused by the thickness of the atmosphere, not the excess of carbon dioxide, as is often suggested in discussions of Earth's global warming. Just a wee aside here, it's Carl Sagan's PhD thesis was actually on the greenhouse effect on Venus. The clouds of Venus may be capable of producing lightning. The existence of lightning in the atmosphere of Venus has been controversial, since the first suspected bursts were detected by the Soviet Venera probes. In 2006 and 2007, Venus Express clearly detected Whistler mode waves, which are the signatures of lightning. Their intermittent appearance indicates a pattern associated with weather activity. According to these measurements, the lightning rate is at least half that on Earth. In 2007, Venus Express discovered that a huge double atmospheric vortex exists at the South Pole. In 2011, Venus Express also discovered that an ozone layer exists high in the atmosphere of Venus. On the 29th of January 2013, ESA scientists reported that the ionosphere of Venus streams outwards in a manner similar to the ion tail seen streaming from a comet. In December 2015, researchers working on Japan's Akatsuchu mission observed bow shapes in the atmosphere of Venus. This was considered the first direct evidence of the existence of perhaps the largest stationary gravity waves in the solar system. Aside from the very surface layers, the atmosphere is in a state of vigorous circulation. The upper layer of troposphere exhibits a phenomenon of superrotation, in which the atmosphere circles the planet in just 4 Earth days, much faster than the planet's rotation of 243 days. The winds supporting superrotation blow at 220 miles an hour or more. As we've seen, or perhaps not seen, the surface of Venus couldn't be explored from orbit using visible frequency optics. Thick and opaque, the atmosphere of Venus required a method beyond optical survey to map the surface of the planet. The resolution of conventional radar depends entirely on the size of the antenna, which is greatly restricted in space by costs, physical constraints, and launch vehicles, and the complexity of maneuvering a large apparatus to provide high resolution data. Magellan addressed this problem by using a method known as synthetic aperture, where a large antenna is imitated by transmitting the data gathered back to Earth before processing by much more powerful computers than could be sensibly located on the spacecraft. The Magellan high-gain parabolic antenna emitted thousands of microwave pulses that passed through the clouds to the surface of Venus, illuminating a swathe of land. The radar system then recorded the brightness of each pulse as it reflected back off the side surfaces of rocks, cliffs, volcanoes, and other geological features as a form of backscatter. To increase the imaging resolution, Magellan recorded a series of data bursts for a particular location during multiple instances called looks. Each look slightly overlaps the previous, returning slightly different information for the same location as the spacecraft moves around its orbit. After transmitting the data back to Earth, Doppler modeling was used to make the overlapping looks and combine them into a continuous high-resolution image of the surface. So rather a long wee section on that, but the reason I'm saying that is we're going to be looking at what looks like photographs of the surface, but it's not. You have to remember pretty much everything we're going to be looking at is a generated computerized figure, just a representation of the data as it was interpreted. And this is the geological map of the planet created from all the data sent back from Magellan. It's rather different from the geological maps that we're used to for Earth, or at least I am, but it can be interpreted as showing that the ground shows evidence of extensive volcanism, and the sulfur in the atmosphere may indicate that there have been some recent eruptions. As far as we're aware, Venus has no active plate tectonics. However, tesserae are a feature unique to Venus, and are characterised as continent-sized regions of high topography, between 1 and 5 kilometres above the average surface height. The term comes from the Greek word for tiled. Tesserae are highly deformed, often with complex patterns of ridges. These areas were formed by the intersection of at least 2 structural components and are classified based on these components. Tesserae are considered to be the oldest surface features on Venus because of their extensive deformation and may reflect conditions on Venus before a global restructuring event. Some of the ridges found on Tesserae terrains, particularly for Ishtar Terra, form large mountain belts. Ishtar Terra is one of 2 main highland regions on the planet Venus. It's the smaller of the 3 so-called continents, and it's located near the North Pole. It's named after the Akkadian goddess Ishtar. The size of Ishtar Terra is roughly between the areas of Australia and the continental United States. On its eastern edge lies the great mountain chain Maxwell Montes, which is 11 kilometres high, compared to Mount Everest at just under 9 kilometres. On one side of the mountain chain is an impact crater, 100 kilometres in diameter, filled with lava. Ishtar Terra contains the 4 main mountain ranges of Venus: Maxwell Montes on the eastern edge, Freya Montes in the north, Arachnoids Montes in the west, and Danae Montes in the south. These surround the lower plain of Ishtar Terra, which is named Lakshmi Planum, after the Hindu goddess Lakshmi. Ishtar Terra also contains volcanoes named after famous women: Sacagawea, Colette, and Cleopatra. Ishtar Terra is also the site of many tesserae formed by tectonic deformation. Aphrodite Terra is named after the goddess of love, the Greek equivalent of the Roman goddess Venus. It's about the same size as Africa and much rougher than Ishtar Terra. The surface appears buckled and fractured, which again suggests large compressive forces. There's also numerous extensive lava flows. Channels across this terrain, and some have an interesting bow shape to them. Aphrodite Terra also has mountain ranges, but they're on about half the size of the mountains on Ishtar. It has 2 main regions: Regio in the west and Thetis Regio in the east. Regio has ridges running in 2 directions, suggesting that the compressive forces were acting in several directions. There's also dark regions that appear to be solidified lava flows. There's cracks where lava is welled up through the surface and flooded the surrounding terrain. Alpha Regio extends for about 1,500 kilometres. It was discovered and named by Dick Goldstein in 1964. Maxwell Montes, Alpha Regio, and Beta Regio are the 3 exceptions to the rule that the surface features on Venus should be named after famous women or goddesses. Like all tesserae regions, it sits above the surrounding terrain at an elevation of 1 to 2 kilometres, and it's heavily deformed by what appears to be contractional folding. Like most tesserae units, the surrounding volcanic plains appear to have flowed around Alpha's margins and are thus younger than Alpha. An infrared map prepared by the Venus Express Orbiter shows that the rocks in the Alpha Regio plateau are lighter in colour and they're cold compared to the majority of the planet. On Earth, such light-coloured rocks are usually granite and form continents. Much of the Venusian surface appears to have been shaped by volcanic activity. Venus has several times as many volcanoes as Earth. It has 167 large volcanoes that are over 100 kilometres across, and 900 other volcanic structures over 20 kilometres in diameter. It's assumed that there's hundreds more smaller ones. These include large volcanic edifices, shield volcano fields, and individual calderas. Each of these structures represents a centre of extrusive magma eruption, and differences in the amount of magma released, depth of the magma chamber, and rates of magma replenishment all affect how they form. When compared to Earth, the number of preserved volcanic zones is staggering, and this is due to the lack of erosion of Venus's strong crust, since it's no equivalent to the freeze-thawing mechanism that erodes mountains on Earth. Volcanic centres on Venus are not distributed evenly. They tend to occur in mid to upper latitudes, where rifting and extension is common, and they signal mantle upwellings to the surface. Volcanic centres on Venus are characterised in two main categories based on the ability or inability to create a shallow magma reservoir. We'll come back to that a wee bit more later. Shield fields are regions 100 to 200 kilometres in diameter that contain many small, mostly shield volcanoes, each less than 20 kilometres in diameter. The only volcanic complex of this size on Earth is the Big Island in Hawaii. Such fields may have 10 to hundreds of shield volcanoes. These fields form in areas where the magma replenishment rate is too low to produce a magma reservoir in the crust, resulting in several small eruptions on a regional scale. The dominance of shield-type volcanoes in these regions has led to the name shield fields. These shield volcanoes are located in Alpha Regio. This is another picture of volcanoes in Alpha Regio, but these have been formed by a completely different process. A pancake dome, also known as a lava dome, is an unusual type of volcano, and this is only found on Venus. They are widely scattered and often form in groups or clusters, though with smaller numbers of pancake domes to each group than is typical for the more common shield volcanoes. They're commonly found near Corona and Tesserae, which we looked at earlier. Pancake domes are between 10 and 100 times larger than the volcanic domes we get on Earth. They have broad, flat profiles similar to shield volcanoes, and they're thought to form from one large, slow eruption of viscous silica-rich lava. They usually have a central pit or bowl-like feature similar to a volcanic crater, but it's thought that these pits form after the eruption as the lava cools and emit gas, rather than being a vent from which the lava originated. The surface of a pancake dome is covered with patterns of small cracks and faults. Single volcanoes denote a single large edifice. Volcanoes of this type include large volcanoes, greater than 100 kilometres in diameter, also named mons, for example, Theamons and Matmons. Intermediate volcanoes from sort of 20 to 100 kilometres in diameter, and calderas. These single eruption centre volcanoes are sustained by a shallow magma chamber in the crust. I just got a thing saying the internet connection was unstable. Are you able to hear me okay, yeah? Somebody could let me know? Yeah, thank you.
Yes, we can hear you okay.
That's great, thanks Janice.
Yep, okay.
So I was saying earlier that magma chambers on Venus are a bit different from Earth. On Earth you tend to get lava welling up quite low down and forming large chambers and staying there. On Venus it tends to come up, as you can see on this diagram, level with the sort of general layer of the surface. So back to the text. On Earth, volcanoes mainly form where one plate slides underneath another. Moisture in the subducted plane thins the rock which rises to the surface and exits through volcanoes. On Venus, this can't happen since there's no floating plates and no water in the crust. On Venus, compressional forces cause the crust to move and crumple, resulting in fold mountains around the edges of the tesserae. Sorry, just checking. On Ishtar Terra, the magma chamber is replenished by magma from mantle upwelling and decompression melting, causing pooling and trapping in a reservoir. This trapping in a magma chamber allows long-term eruption and results in magma flows that may create large volcanic domes and flow deposits. The shape of the dome or magma flow field is determined by the chemistry and the viscosity of the magma. Another feature of Venus are plains, again similar to Earth, but not similar. Plains are large areas of relatively flat topography in Venus that form at varying elevations. Plains cover about 80% of the Venusian surface, and unlike those seen on other silicate planets, they're heavily faulted and fractured throughout. Structurally, These plains contain features such as wrinkle ridges, fractures, scarps, troughs, hills, and dikes. Plains often contain visible flow patterns, indicating a source from volcanic lava flows. The presence of surface flow patterns in conjunction with cross-cutting valleys has given rise to the hypothesis that these plains probably formed by global lava flows over a short timescale and were subsequently exposed to compressional and extensional stresses. This is a radar mosaic from Magellan showing a 600-mile-long segment of the Baltus Vallis, a channel on Venus that's longer than the Nile. The surface of Venus contains over 200 channel systems, named valves, that resemble terrestrial rivers. These channels can go up to 7,000 kilometers long and up to 30 kilometers wide. Their global distribution isn't uniform, and they tend to concentrate around the equatorial region near volcanic structures. They also show characteristics of flows, such as levees on the margins and downstream narrowing and shallowing. Channels also don't contain tributaries, despite their large scale. However, because of the high surface temperature of Venus, making a comparison with terrestrial rivers is difficult. These features are similar to lava flows on other terrestrial planets, which has led to the conclusion these valleys probably were formed as volcanic flows. This is also suggested by the evidence of cooled lava flows filling the valleys. Channels likely formed in very short timescales of 1 to 100 years, indicating very fast movement and erosion of lavas. There's 3 types of valve. Simple channels, so I just need a wee drink. Simple channels are single channel valleys with little or no branching. Types of simple channels observed on Venus include sinuous rills, simple channels with flow margins, and canali. Sinuous rills are like those seen on the Moon, narrow erosive channels that originate from regions of volcanic collapse. Simple channels with flow margin are located in obvious flow fields with an undefined source and end, and are believed to feed into large flows with surrounding volcanic features. Canali, like the Baltus Vallis, are long flows with constant width and depth that may contain abandoned channels, bends, and levees, indicating their source from large amounts of thick lavas. Complex channels are channels that can be braided or distributed patterns. They commonly form on lava flow deposits, and their individual channels are separated by islands of crust. Compound channels show simple and complex channel structures. These channels usually begin as simple channels and fork and meander as flow energy decreases. This image here is the channel left by lava flowing from Fortuna Tessera to Sedna Plantinia. These photographs obviously weren't taken on Venus, but have you seen, lava flows in Venus are often much larger than Earth's, up to several hundred kilometers long and tens of kilometers wide. It's still unknown why these lava fields or low-wake flows reach such sizes, but it's suggested that they're results of very large eruptions of basaltic, low-viscosity lava spreading out to form wide, flat plains. On Earth, there's 2 main types of basaltic lava, A'a and Pahoehoe. A'a lava presents a rough texture in the shape of broken blocks or clinkers. Pahoehoe lava is recognized by its pillowy or ropey appearance. Rough surfaces appear bright in radar images, which can be used to determine the difference between oops, sorry, somebody wants in, just gonna let them in. Rough surfaces appear bright in radar images, which can be used to determine the differences between A'a and Pahoehoe lavas. These variations can also reflect differences in lava age and preservation. Channels and lava tubes are very common in Venus. This may be explained by the very fluid lava flows together with the high temperatures in Venus, allowing the lava to cool slowly. I had this problem last time I let somebody in. I have to just do something else to change the button and then I can get back on my clicker. Another interesting unique feature on Venus's surface are novae, which are radial networks of dikes or grabens. A nova is formed when large quantities of magma are extruded onto the surface to form radiating ridges and trenches, which are highly reflective to radar. These dikes form a symmetrical network around the central point where the lava emerged, where there might also be a depression caused by the collapse of the magma chamber. Arachnoids are so named because they resemble a spider's web, featuring several concentric ovals surrounded by a complex network of radial fractures similar to those of a nova. It's not known whether the 250 or so features identified as arachnoids actually share a common origin, or perhaps they are the result of different geological processes. To create such lava flows requires huge volcanoes, and this is the image of the 175 kilometre wide Isabella crater, surrounded by lava flows. Located on Ishtar Terra, the more northern of the planet's two major highlands, Maxwell Montes is 11 kilometres high. It rises about 6.4 kilometres above and to the east of the planetary plenum, and it's about 853 kilometres long by 700 kilometres wide. The western slopes are very steep, whereas the eastern slopes descend gradually into Fortuna Tessera. Due to its elevation, it's the coolest. It's only about 380 degrees centigrade, very cool for Venus, and the least pressurized location on the surface. The origin of the Kashmir planum and the mountain belts such as Maxwell Montes is controversial. One theory suggests they formed over a hot plume of material rising from the interior of the planet, while another says that the region is being compressed from all sides, resulting in material descending into the interior of the planet. The broad ridges and valleys making up Maxwell Montes and Fortuna Tessera suggest that the topography resulted from compression. The parallel ridges and valleys were cut by later extensional faults. The extreme height of Maxwell Montes in relation to other compressional mountain ranges around Lakshmi Planum suggests that its origin is more complex. So if we look on the right-hand side of this, it looks like snow on the side of Mount Everest or somewhere like that. Most of Maxwell Montes has a bright radar return, which is common in Venus at high altitudes. Venus snow is a brightening of the radar reflection from the surface of Venus at high elevations. The nature of the snow is initially unknown. In radar images, smooth surfaces such as lava plains generally appear dark, while rough surfaces such as impact debris appear bright. The composition of the rock also alters the radar return, making conductive material appear brighter. It was therefore initially difficult to determine whether the high altitude areas of Venus were different from the lowlands in chemical composition or in texture. Possible explanations included loose soil, different rates of weathering at high and low elevations, chemical deposition at high elevation. It couldn't be water ice because there isn't any water on the extremely hot, dry conditions of Venus. Data from the radar mapper on the Pioneer Venus orbiter suggested an explanation in terms of chemical composition. It was suggested that the underlying rock contained iron pyrites or other metallic conclusions that would be very reflective. At the high temperatures found on the surface of Venus, these minerals would gradually evaporate. Faster weathering at high elevation might continually expose new material, causing the highlands to appear brighter than the lowlands. High-resolution radar observations by the Magellan probe began to favour the idea that metallic compounds sublimate in lower, warmer altitudes and then deposit in the higher, cooler areas. Candidates of the metallic compounds included tellurium, pyrites, and other metal sulfides. Sachs Patera is an unusual feature on Venus. Defined as a side caldera, Sachs is an elliptical depression 130 metres deep, spanning 40 kilometres in width along its longest axis. The morphology implies that a chamber of molten material drained and collapsed, forming a depression surrounded by concentric scarps, spaced 2 to 5 kilometers apart. The arch-shaped sets of scarps extending out to the north from a prominent ellipse is evidence for a separate episode of withdrawal. The small lobe-shaped extension to the southwest may represent an additional event. Solidified lava flows, 10 to 25 kilometers long, give the caldera its flower-like appearance. The flows are a lighter tone of grey in the radar data because the lava is blockier in texture and consequently returns more radar waves. Much of the lava evacuated from the chamber probably travelled to other locations underground, while some of it may have surfaced further south. This is unlike calderas on Earth, where a rim of lava builds up in the immediate vicinity of the caldera. This figure shows the volcanic peak Idnan Mons in the Indra Regio area of Venus. The volcano has a diameter of about 200 kilometers. The topographic backbone derives from data obtained from NASA's Magellan spacecraft, with a vertical exaggeration of 30 times. Radar data in brown from Magellan has been draped on top of the topographic data. Bright areas are rough or have steep slopes. Dark areas are smooth. The coloured overlay shows the heat patterns derived from surface brightness data collected by the visible and infrared thermal imaging spectrometer aboard the European Space Agency's Venus Express spacecraft. Temperature variations due to topography have been removed. The brightness signals the composition of the minerals that have been changed due to lava flow. Red-orange is the warmest area, purple is the coolest. The warmest area is centred on the summit, which stands about 2.5 kilometres above the plains, and the bright flows that originate there. So the reason they think this is evidence of an active volcano is obviously that the centre of the planet is still hotter even in the atmosphere. So what you're finding is the higher something up is in Venus, the cooler it tends to be, as we saw earlier. And yet in this case, the hottest, the reddest bit, is at the top of the structure. So that has to indicate something hot has come out of it, hence a possible active volcano. Impact craters are roughly circular shaped depressions on the surface of the planet due to high velocity impacts with extraterrestrial bodies. The surface of Venus contains almost 1,000 impact craters. However, unlike some planets in our system, Venus's thick atmosphere creates a strong shield that decelerates, flattens, and can even fracture incoming projectiles. The Venusian surface is devoid of small craters, from 30 to 50 kilometers in size. It's pretty huge by Earth standards, because of the effect the atmosphere has on the small bodies coming in. Depending on the angle of impact, velocity, size, and strength of the approaching body, the atmosphere may tear and crush the projectile, essentially melting it in the air. This is a complication when studying the surface of Venus, since in planetary science, impact craters are used to determine relative ages and to approximate absolute ages of surface features. Craters on Venus are kept in pristine condition, thus making their classification and impact mechanics easy to interpret. As I said, small projectiles burn up in the atmosphere, and those that do make it to the surface break into smaller pieces, creating clusters of impact craters, similar in appearance to circular lunar craters. As crater size increases, the chance of breakup in the atmosphere decreases, and the impact craters become more circular, with central peaks from isostatic rebound of the crust. The atmosphere can flatten and show larger reshrides to terminal velocity and cause them to explode on impact or near the surface, showering the region in debris. The shock waves from these explosions can flatten the surrounding area for several kilometers. Large impacts create parabolic excavation cones and flows of lava like debris. New crust on Earth gets built horizontally, thanks to the lateral motion of the spreading centres. Without such spreading, new crust on Venus has to be built vertically. On Venus, The crust gets thickened by the top of volcanism and on the bottom by slowly cooling magma reservoirs. This process builds a thick and correspondingly strong basaltic crust that grows thicker over time. Such a strong crust resists deformation, even if Venus's mantle flows and circulates under the crust like Earth does. Without deformation, plate tectonics can't start. Plate tectonics plays a crucial role in Earth's geology. The churning of the solid rocky mantle, with hot material rising from deep in the interior and causing volcanic eruptions at the surface, efficiently moves heat from deep within the Earth out of the planet and out into space. On Venus, without plate tectonics, heat has no quick route out of the interior. The planet generates interior heat in the same way that Earth does, by freezing of the core and radioactive decay. But on Venus, the heat has nowhere to go. It builds up and the mantle starts to melt. If there continues to be no heat release, it's possible for large sections of the mantle to melt relatively quickly, generating a massive reservoir of magma at the crust-mantle boundary, and then this erupts. Many more specific mechanisms have been posed to produce global volcanic catastrophe, but each one of them has the same basic idea in common: massive, all-encompassing destabilization of Venusian mantle, producing a correspondingly massive response, and the release of all that magma as volcanism, to return things thermally to business as usual. When this happens, Venus returns to being a slowly cooling, mostly stagnant planet. It's possible that it might already have cooled to the point where such resurfacing events may never happen again. Again, you probably guessed this isn't on Venus. Water is almost non-existent on Venus, and thus the only erosive process to be found is the interaction produced by the atmosphere with the surface. This interaction is present in the injecta of impact craters expelled onto the surface of Venus. The material ejected during a meteorite strike is lifted to the upper atmosphere, where winds transport the material towards the west. As the material is deposited on the surface, it forms parabola-shaped patterns. This type of deposit can be established on top of various geological features or lava flows. Therefore, these deposits are the youngest structures on the planet. Images from Magellan reveal the existence of more than 60 of these parabola-shaped deposits that are associated with crater impacts. Unfortunately, despite over an hour of trying, I couldn't find a picture of any of those parabola-shaped deposits. The ejection material, transported by the wind, is responsible for the process of renovation of the surface at speeds of about 1 meter a second. Given the density of the lower Venusian atmosphere, the winds are more than sufficient to erode the surface and transport fine-grained material. In the regions covered by ejection deposits, there are wind lines, dunes, and yardings. The wind lines are formed when the wind blows ejection material and volcanic ash, depositing it on top of topographical obstacles such as domes. As a consequence, the leeward side of domes is exposed to the impact of small grains that remove the surface cap. Such processes expose the material beneath, which has a different roughness, and thus different characteristics under radar compared to the formed sediment. The dunes are formed by the deposit of particulates that are the size of grains of sand and have wavy shapes. Yardings, like the picture of this one on Earth, are formed when the wind-transported material carves the fragile deposits and produces deep furrows. Recent Magellan images show over 6,000 wind-formed landforms, including dunes, wind streaks, and yardings. Dunes and yardings have direct analogues on Earth, and the process that creates them here can be applied to those seen on Venus. Large dune fields have been identified at the surface, and the dunes range in size from meters to hundreds of meters. Similarly, yarding fields may exist in locations such as Meade Crater. Wind streaks are parallel linear streaks that form as prevailing winds, eroding the surface geology. These features illustrate the erosive effects the atmosphere has on the surface of Venus. NASA's Goddard Institute for Space Studies and others have suggested that Venus may have had a shallow ocean in the past for up to 2 billion years, with as much water as Earth. Depending on the parameters used in their theoretical model, the last liquid water could have evaporated as recently as 700 million years ago. Currently, the only known water on Venus is in the form of a tiny amount of atmospheric vapour, about 20 parts per million. Hydrogen is still being lost to space in modern times, as detected by ESA's Venus Express spacecraft. We're expending a lot of time and effort sending missions to Mars to try to discover traces of ancient life forms there. So is it possible early forms of life could also have survived somewhere on Venus? In September 1967, Carl Sagan suggested that life could have survived in the cloud tops of Venus, where the temperature ranges from 65 to minus 20 degrees centigrade. As I'm sure you're aware, and as we talked about before we started tonight, research published in September 2020 indicated the detection of phosphine in Venus's atmosphere. As far as we're presently aware, this gas cannot be produced in Venus's atmosphere by anything other than biological processes. It's also not expected that a molecule like phosphine can persist in the Venusian atmosphere for more than a few weeks, since the ultraviolet radiation would cause it to react with water and carbon dioxide and break the molecules apart. This suggests that there is some process that is causing it to be continuously produced. Phosphine is created in anaerobic ecosystems on Earth, and it's therefore considered as a possible biomarker. The discovery of phosphine also gives a potential explanation to the dark streaks on the surface of Venus detected by the Japanese Space Agency, which could be colonies of microbes living in the cloud layer. Extraordinary claims require extraordinary levels of proof. So it's worth noting that Professor Jane Greaves and her colleagues followed the highest levels of scientific practice by first looking for and detecting phosphine using the James Clerk Maxwell telescope in Hawaii and analysing the results with one type of mathematical analysis. She then convinced a completely separate team at the Atacama Large Millimeter Array in Chile to perform the same search, but using their own independent analysis of the results. Both methods indicated the presence of phosphine, so in science, this is good enough evidence to publish. However, the detection of phosphine will not be considered factual until other teams of scientists, using their own methodologies, also confirm both the presence of the gas and the lack of any other geological process that could create it on Venus. So we might have to wait a while for any definitive proof of simple life forms being created anywhere except on Earth. It would take a long time for NASA or any of the other national space agencies to approve and send a spacecraft to the planet with a specific task of detecting the source of phosphine. However, as luck would have it, Rocket Lab, a private small rocket company founded in New Zealand, has been working on just such a mission. The company has already developed a small satellite called Photon that it planned to launch on its own Electron rocket as soon as 2023. Peter Beck, Rocket Lab's founder and chief executive, said, "This mission is to go and see if we can find life. Obviously, this discovery of phosphine really adds strength to that possibility. So I think we need to go there and have a look." Usually when I talk about geology, it's with regard to processes that continue for millions of years. So it came as a bit of a shock to me to discover such a major difference in the way we think about the possibility of life on Venus. It changed completely in the last 2 weeks. Not many pretty pictures in this presentation, I'm afraid to say, but hopefully I've helped you to understand that Venus is more than just a fuzzy ball of light in the sky. As you know, I'm not an expert, but if you've got any questions, I'll try and do my best to invent an answer. Thanks a lot for listening.
Thank you.
Thank you.
Could I say something?
Yeah, please do, Eddie.
Many moons ago, I was looking at all these pictures of Venus, and there's a lot of false colour in them.
Uh-huh.
I think the first one showed traffic light colours, reds, there was blues, there was greens on Venus.
Yeah.
And a lot of them have come since, showing shades of yellow. And I did try and inquire, I think it was the astronomers at Bristol University. I tried to find out what would Venus have looked like umpteen million years ago during its active stage without the clouds. What colour would you have seen? And they came up with some ideas, and I actually made a globe of Venus, trying to put in what it would have looked like to an observer from Earth with quite a great big telescope, looking at Venus during its active stage. I don't know if this will show up on the screen.
Oh yes, it does. Right.
This is a globe I made. Well, I think it's not very clear, is it?
Oh, that's good. I can see
Oh,
it.
that's good.
Excellent.
I can see it. Oh, that's
See the
marvellous.
colours.
Yeah,
It's good. Good.
that's brilliant.
It's not showing up too well.
Wow.
Perhaps if I move my iPad around.
Brilliant.
That's brilliant, that.
Yeah.
Let's see if I can stand up a minute. What can you see now? Where's it gone?
Disappeared.
Disappeared, isn't it?
Yeah. Yeah. We saw it better.
Let's try something else. It needs to be a long way further away, I think.
Oh, we can see a wee bit of it now.
Aye.
Um,
Well, that's brilliant. Yeah.
It would have been browns.
Yeah.
The red is the erupting volcanoes. It's actually a 3D. This actually is a lot of thick, gluey stuff I put there. So it is actually 3D.
Uh-huh.
You would have seen shades of red, brown, grey, where all the lava is cooled in. The lava would have been dark grey probably, or blackish.
Right. That's brilliant.
That's brilliant. Aye.
I love it. Yeah.
Aye.
Not too good.
That's really good, that.
I'll send you some photographs. Would that be better?
Yes. Yes,
Yeah.
that'd be great, Eddie. Thanks. Yeah, that's really good, that. I mean, very impressed.
And up towards the North
Wow.
Pole.
Yeah.
Aye. I mean, considering I can't even draw a straight line with a ruler, I mean, that is brilliant, that. Really good.
Yeah.
I'll send them 3 or 4 photographs. I don't know if you can send it out to the members.
It's amazing. Love it. It's
Yeah.
great. Brilliant.
Yeah, that's more what it looked like without your false colour.
Oh, that's well done.
Aye.
Well done.
A lot of the red would have been erupting. The yellowy colours would have been sulphur coming out of the volcanoes. A lot of the lava here, so a lot of lava. A lot of lava. Well, I think it's better if I send you some photographs.
Yes.
I don't know if
That's
you
really good.
can send them out to members.
Yes. Yes.
Brilliant.
Well, that's really good.
It was an old Earth globe that I painted over years ago.
Ah, right. Right.
You got Pete Williamson in, is it 2 or 3 weeks' time?
Aye, the 5th of October, so 2 weeks' time.
Right. I will do an anniversary on another Cornish astronomer, but at the beginning of Pete's talk, it might have been his first, second or third slide he put up. I noticed a mistake with a date. And I pointed it out to him at the end, and he said, "Oh, I blame that on Wikipedia." So if you see this, if you watch his talk, which is excellent, just notice at the beginning, first, second, or third slide, he's put up on the screen an incorrect date, which he didn't know. So perhaps some of you can point it out to him at the end.
All right.
So look out for that date right at the beginning.
Right.
Okay then.
Right.
Okay.
Thank you.
Okay. I'm
Thank
going
you.
now. I'm going now to get on the phone to one of my daughters.
Right.
Yeah.
Okay. All the best, everyone.
Yes.
You too.
All
Thank
right.
you too.
Thank you. Bye-bye.
Right. Bye.
Cheerio. Bye.
Bye, Eddie. Bye. Any more questions for Roy?
Just one. Where you were showing the wind effects on rocks, those of course will be artist's impression value taken from the radar reflection.
Which one? Sorry, the Ardang I was showing earlier.
Sorry?
The colour, when you're talking about the wind erosion.
Yeah, the wind erosion, you showed a colour slide showing the sort of rock formation with the wind erosion.
Ah, yeah, that's in the desert of Oman.
Is that an artist's impression? It's not a
No, that's actually a rock in the desert in Oman.
Okay.
A thing called a Yardang. So obviously we don't have any close-ups of the surface of Venus.
Well, I knew
I
that.
was just trying to show you something that showed erosion patterns on a rock.
Yeah.
That's one of the problems with, again, I originally did this talk about 2 years ago. I think it was actually at the AGM for Clydesdale, and it was just a quick half-hour presentation. So when I was going to do the longer version for tonight, I spent quite a lot of time searching through, trying to get the best high-definition images I could, but also a bigger variety of images. And there's actually very few, to be honest, if you've ever looked through.
Yeah.
And it's because of that, you know, I'm on screen for a minute or two while I talk, because there just aren't any examples of actual surface features to be seen.
I still think it's fantastic that from the radar reflections and images they get from that they're able to deduce so much about the internal structure of the planet.
I think, again, that's one of the big problems. Because the surface temperature is how hot, it's going to be incredibly difficult to figure out if it's still got a liquid core, or, you know, whether there has been any tectonics or anything like that, because the surface temperature at its height, you know, just masks almost anything that's happening underneath the surface. Tricky. But no doubt somebody will come up with a very clever way and figure out how to do it in the same way they did with the side scan radars.
I know when I was making up my talk about volcanoes in the solar system, trying to find, like what you're saying, decent images, the wow factor images, you know, for Venus, it took hours to try and find these images. You know?
Did you see any geology from the photographs that Venera probes took?
I'm not sure, Jim, to be honest. I don't know. I think I showed a couple of the early slides were Venera, but I couldn't be specific about anything. I think of the continents, but that was about it. Just the major features.
Roy, you were talking about the surface temperature of Venus being whatever, 400 and what have you. Is that the daytime temperature?
Well,
maximum. And if so, what does the nighttime temperature drop to?
Well, you don't really
seeing
get
as it's such a long day.
Yeah, well, it's not so much that, because the atmosphere is so thick, and because a day is longer than a year, you don't really get one side of the planet heating and the other side cooling. There's a constant high wind that rotates the heat and mixes the heat all around it. So I think it's pretty much the same temperature all the way around all the time. It's my
fan-assisted oven.
Yeah.
Aye, because it's a runaway greenhouse.
Yeah.
A runaway greenhouse system.
Yeah, it's only a runaway greenhouse to the extent I tried to explain earlier that it's carbon dioxide being left behind, but it's not carbon dioxide that makes it hot. It's the pressure that makes it hot.
Yeah.
You know, listen, I get slightly annoyed sometimes on the telly when they keep going on, oh, if we don't do something about global warming, it'll be like Venus. No, it won't. Yeah, there's a lot of things global warming is going to do, but it won't make the planet like Venus.
Do we have any idea how it will progress over the next few billion years? I mean, obviously it'll be vaporized eventually by an expanding sun, but that's a long time hence. So what's its prognosis? Will it just carry on getting hotter or what?
Well, again, I'm not too sure on that one, because one of the things that was mentioned was that it was suggested that the core might have already gone solid, in which case there's going to be less heat coming from inside. So if anything, it might start to cool rather than keep getting hotter.
Haven't they discovered some volcanoes that are still active? Didn't I read that?
Well,
recently?
I showed that. That was one of the slides I showed.
Yeah.
Where the top of the volcano is in red.
Yeah.
Yeah, I mean, again, there's the difference between the core of the planet and magma chambers up nearer the surface.
Right.
So if the core had already frozen, it wouldn't stop magma being available still at the surface. But again, so it's not me because I don't know enough about it, but one of the suggestions was that the major resurfacing events, there may not be any more of them because, you know, the planet's already cooled to the extent it couldn't happen again. But because the surface temperature is so high, it's going to be very, very difficult for anybody to have anything other than just theories and something like that. We just don't know.
Right.
Yeah, have we got any idea of the sort of chemistry of Venus, such that we can make some idea of or get some idea of the mineralogy of the rocks and magma that are moving about there?
Again, I certainly haven't seen anything about it. I think because all you do, I mean, they have, or again, one of the slides mentioned things like they reckon the snow in Venus is a tellurium or iron pyrites that's evaporated. But again, what they're really just doing is guess a metal with a fairly low melting point. If it was at a slightly lower temperature, would go back to being a solid again and therefore give you the Venus snow. But I think it's, you know, it's all very theoretical as my understanding of what they're saying.
Well, like theoretical guesswork sort of thing, but theory nonetheless, or a hypothesis.
Yeah.
To know what the surface would be, you need to see a spectrum, and you can't see directly the light from the surface, so you can't ever see a spectrum.
Exactly. Yeah. It's not possible. So, I mean,
could I ask a question, please?
Sorry, yeah.
Yeah, it's Hugh Somerville from the ASE. First of all, on behalf of the other members, I see there's about half a dozen of us are watching. It's a fantastic talk, absolutely fascinating. I was wondering if the Soviets did anything in the way of protecting the Veneria craft, or did they was it just wish it good luck and hope it survived for a few seconds or minutes?
No, I think it was the opposite. I think they did design it to be a complete tank.
Yeah.
Unfortunately, even a complete tank doesn't stand a chance on the surface of Venus. You know, it is so hostile there, so incredibly hostile. And as I did mention, but I don't know if you picked up on, the temperature there is so hot that solder melts, and all the electronic components are held together by solder. So if the electron
melts, never mind solder.
In fact, it's
470 or something, isn't it, centigrade?
Yeah, well, it's 480, I think, on the surface of the planet. You know, whereas a match can melt solder out through much problem. So it's astonishingly difficult to be there. But what they have talked about doing, and I think there's certainly plans afoot in NASA, is you actually send a balloon. So there's no attempt to get on the surface. I mean, don't be silly, don't even try and do it. But they reckon a balloon could float around up there for years. Again, because the atmosphere is so dense, you know, when I'm talking about a balloon, you're probably talking something that looks, you know, like a great big ball. That probably looks more like, you know, the sort of thing you put down at the bottom of the ocean. But, you know, just a good strong metal ball will float quite happily. You know, sort of 20 or 30 miles up, and the wind, as we said earlier, it travels about 200 miles an hour. So you've got a free way of getting something to travel around the entire planet. So I'm pretty sure that will happen.
Do we have any indication of the temperature at the visible cloud level that we see, to get an idea of the temperature gradient going down? I was wondering if the gas near the surface might actually be hotter than the actual surface itself, you know, with the winds taking the atmosphere around.
I don't know anything on that, I'm afraid, sorry.
We don't know.
Well, I don't know, but I haven't
know the
seen anything about that while I was looking for
the
it.
surface of the clouds.
Yeah.
Did that Russian spacecraft measure temperature as it went in? I don't know.
I'm afraid I didn't check that one out. I don't know.
No idea either.
I saw a report about the phosphine that was found recently, and it suggested that, quote, I'll just quote, that the temperature at which the phosphine was found was what they called shirt sleeve temperature.
Yeah, right, okay.
So I presume that's sort of 20, 30, 40, something that we could live with.
Yeah.
And that's 50 or 60 miles up.
Oh.
Yeah. You'd expect a big temperature gradient down through a dense cloud like that.
Okay.
Any more questions? Because I can never think of one.
So, I can never think of the answer anyways.
So I'd like us to thank Roy in the usual way for his excellent presentation. It was very interesting, you know, and I've taken note of some of the crater names and that, just in case I update my Volcano and the solar system talk anytime. Right, so...
Very interesting.
Thank you very much.
Thank you, Roy.
Yeah.
Alison, Mandy, do you just want to stay on for a chit chat, or sure?
Aye, that's fine, aye.
I need to disappear to the loo, so chat amongst yourselves.
Is Robert still there?
Yeah.
Have you sorted out agenda for the AGM? Pardon?
The minutes are done.
Thanks very much for inviting us from Edinburgh. But I'll have to
All right, no problem.
That was a really good talk. Thanks. Sorry to interrupt.
No, that's fine. No, I'll invite you again for the next one and that as well.
That'll be super. Great. Thanks
Right.
Thanks very much.
So if you put the agenda, I know you're saying you've done the minutes. So is that the agenda then for what? Aye, that's my brain's away.
The agenda's usually just half a dozen items, and it's always the same format, you know.
Aye.
Unless you get additional questions or additional questions.
Right. So I mean, if you send me the minutes and the thing, and then I can.
Go in another room. I'll go and get it and put it in this computer.
Aye, and that way, either yourself can attach it to an email for the members, or I can do it.
Well, I'll send you Alice, Amanda.
Aye.
Yeah.
If you send it to the Clydesdale Astronomical Society email address, then I can just forward that on to the members.
Okay.
Right, that's lovely.
Alice, Amanda, I got the audited accounts back from John Gallagher yesterday.
Right.
So I'll send
This is still getting
a copy
recorded,
of the
by
accounts
the
over. You
way.
can send them out at the same time.
Right.
This is still getting recorded, by the way.
Aye, it'll be fine. Aye.
This is still getting recorded.
Yeah, I was thinking that. I'll just stop
By the way.
Hold on a second.